Hello fellow Scratchers, I'm Griffpatch and I am super excited to get right into coding our Raycaster today. Oh my gosh, yes! I hope you enjoyed designing your levels and are ready to go because we have so much to cover today. We'll be creating light rays, light beams with Godrays, that is in itself such a joy to play with, basic 3D projection and finally a lens corrected, shaded render of our level. Wow! Oh come on, let's get scratching! And so we continue straight off from where we left our projects in episode 1. Our levels are designed and we can walk around first-person style using the WASD, WASD and cursor keys. Right then, Raycasters. They're called as such because they work by sending out rays of light from our player in straight lines across the level to find where they collide with walls. Casting rays. A good place to begin then is with the process of casting, or firing out one ray. To do this, we'll need a new sprite, but rather than starting from nothing, we'll instead duplicate the player sprite. Now rename it Raycaster, and then we can delete all the blocks. Yeah, we don't need these. Next, go into the Costumes tab, and also delete the player costume. So the only thing we are keeping is the little hitbox costume from episode 1. Right, on we go. Let's set up the raycasting sprite. When flag clicked, switch it to our hitbox costume. And we'll set the rotation style to don't rotate. Doing this will ensure the touch sprite sensing blocks are as consistent as possible. For now, we'll fire off a new projectile when the space key is pressed. We want to fire the projectile the same direction the player is facing. So point in direction. Now to get the player's direction, we look in the sensing category and get the elusive thing of thing block, a tricky block to find, but ever so useful. Now switch the right side to read player, and the left side can then be set to direction. So point in direction, direction of player. Great. Now for its position. Easy. Go to player. Quick test, and this is doing what we expect. We should find that every time we press the space key, a little square hitbox costume is positioned just at my player's feet. Not so exciting. So let's set it off moving, like a projectile, until it collides with the level. So repeat until we are touching the level. And until we do, we just move the projectile forwards with a move 4 steps. Now before I explain why I chose 4 steps here, let's give this a quick test. Smash that spacebar. And off it goes, trundling in a straight line across the level. And when it hits the wall, it stops. The repeat loop is ended. Now remember I told you to make sure the level was fully surrounded by walls. I hope you listened, because if not, this projectile loop would never end. Right now, that's not such a big problem. But later on, that will cause great lag. So be warned. Coming back to that move 4 steps. How did I come to that number? Well, obviously, a smaller number would mean the projectile would move slower. You can try it if you like, but when creating a Raycaster, one thing you do not want is a slow project. Speed is everything. So then, why not bump this number right up to say 16? Well then, the projectile would move in such large steps that it can skip right over a wall without colliding, and that would be bad news for us. So we need to find the largest step we can take that will not have this problem. Well, if we look at our costume, we see that it's 4 pixels wide. Therefore, if we move by anything more than 4 pixels, we will be leaving gaps between the sensing locations. So 4 is the biggest step we can safely move. Moving by 4 pixels does have the benefit of getting the projectile across the level quicker. But a disadvantage is that it can leave the projectile deeply embedded in a wall. Luckily, we can deal with this by carefully reversing it back out again so that we find the true point of collision. To do this, duplicate the existing repeat block, and this time we repeat until we are not touching level. And to reverse slowly out, we need to move by -1 step. Perfect. Want to see that in action? Sweet! Each projectile now ends up very nicely flush up against the wall, no overlap to be seen. I find it quite funny though, that if you look closely, you can see the projectiles wiggling back out of the wall after they've collided. That's because we are not using any run without screen refresh blocks. That means every move we make in a repeat loop is being animated. Well, we'll stop all that animation now anyway. Make a new block and name it Single Ray. And we make sure to tick the run without screen refresh. Okay, move everything below the point in direction block into our new define block. And then drag in a new single ray block to where we move the scripts from. So where before we were animating the flight of the projectile, now we have wrapped the entire process in a run without screen refresh. Boom! The projectile finds the wall instantly. And we can change direction, and at every press of the space key, our projectile just materializes at the point of collision. Very neat indeed. What we've created here can be thought of as a line of sight raycast. It shows us what is directly in front of the player. A fun enhancement to this might be to draw the line between the player and the collision, like a laser gun. So, have you ever used the pen extension before? Just click on the Add Extension button down here, and add Scratch's pen extension. Sweet! A whole new category of Scratch blocks to play with. To avoid ending up with a screen full of lines, drop an Erase All block in to begin each shot. Next, we set pen size to 4 to keep the width of the line similar to our projectile. And then set the pen colour to 53. This is a hue colour and should be a nice Jedi blue. Then to draw the line itself. Within the single ray script, after the go to player, we drop in a pen down. Now every movement of the sprite will leave behind a line. So then pop a pen up at the bottom of the script as we've finished moving. Super! Let's test! Hit the spacebar. Zap! What a beautiful blue laser gun we have made. That works really well, and we can rotate and shoot it off again. And again. The lasers trace from player to wall instantaneously, and with very good precision. You getting any ideas for awesome games you could make with this? Seriously, there's so much we could do with the things we cover in this tutorial. It's one you'll find you can keep coming back to again and again. Okay, the next step is to go real time with the laser gun, changing it into a laser beam or laser pointer. So no more when space key pressed. Bring in a when I receive block, and we'll make a new message named Raycast. Swap all the scripts from the space key over to that, and now all we need to do is broadcast this event. So click into the player sprite. Now locate the bottom of the main forever loop and just pop in a broadcast Raycast. Okay, so how beautiful is this? I feel like we need a bright spark on the end and a sizzling sound as we cut a big chunk of level away with this huge, awesome laser beam. Each step of this tutorial brings with it fun new toys to play with. This is just too cool. So, moving fast now. We've done a single beam. How about we widen it out to make a full spread, like Godray-like? No problem. Surround the single ray block with a repeat. Yeah, for 10, why not? But we need to turn within the loop so that the rays are spread out apart from each other. Turn clockwise, that's to the right, by 5 degrees. But this repeat needs to be within a run without screen refresh too, otherwise it just won't work. So make a new custom block, naming it Raycast, and tick the run without screen refresh. The repeat 10 goes in there, and drop a Raycast block in where we move the scripts out from. Splendid! I'm feeling good about this. Run the project. Oh man, that is cool. I like it a lot. It reminds me of a laser show at a concert. Each ray emits from the player and individually finds the furthest point it can travel to before it collides. You get some really interesting patterns being cast by these rays now. So no problem here, things are still running really smoothly. Shall we try and up the number of rays even more? We'll begin by making a variable to define the spread of rays that we want to generate. Name it FOV, for all sprites. That stands for Field of View, and will be useful for raycasting later on. But for now, we can think of it as the spread out of the rays. Under the When Green flag clicked, set FOV to 60. That's a good standard setting. That will work well for us later on. However, for extra entertainment, right-click the FOV reporter on the stage and make it into a slider. Then I'll set the minimum value to 30 and the maximum to 120 degrees. Nice. Now, back in the Define Raycast. We'll use the FOV variable as the number of times we repeat. Wow, that's going to be a lot of rays now, 60 of them. And since there are so many, we'll reduce the turning angle to just 1 degree to squeeze them all in, leaving less of a gap. It's testing time. Oh wow, the rays are so tightly packed that they have formed what looks like a solid flashlight beam. That looks so amazing. And watch this, I can adjust the FOV slider to expand and contract how wide the beam is. So neat. But do you see a problem we have here? The beam is not centered on our player. Instead, it's always being sent out to one side of us. To fix this, we need to rotate the whole beam half of its width to the left, counterclockwise. Okay then, before we start drawing the beam, add a turn left block, and half of the beam is easy to calculate. It's FOV divided by 2. That's the ticket. The beam is well centered. And you can see it clearly as we play with the FOV slider. So cool. I could play with this like forever. What I especially love is to watch the shadows being formed by these light rays as I move, rotate and strafe around the level. Look at the shadows cast by the little pillars. They are particularly cool, don't you think? Well, if that doesn't get your imagination flowing, I don't know what will. But we are not done yet. Not even close. For now, we are going 3D. Are we excited? Oh yes. Take a look at this example scene. Up until now, we've been using this blue beam to represent light shining from our player into the level. And I've talked about this being the player's line of sight. That is, everything our player can see. So, for example, the player can see this front wall here, but won't be able to see through it to the wall behind. In this scene, we can identify 5 distinct wall sections visible to the player from this viewpoint. If I pull up a 3D view of the scene, we can clearly see the same 5 matching sections. So how do we go from our 2D raycast to a 3D view? Well, let's slow down the raycasting and watch the scene build one ray at a time. We cast out rays from left to right as before, making a note of just how far a ray had to travel before it collided with a wall. This tells us just how far away the wall is in that direction. And so, when we begin to draw a 3D scene, again from left to right, we know we need to paint a slice of wall, we just need to know how tall to draw it. A close-up wall is large, and a faraway wall is tiny. This is called perspective, and it's a simple concept. To be precise, an object that is twice as far away appears half as big. That is, perceived height is equal to size divided by distance. Using this idea, we raycast and draw an entire 3D scene, one ray at a time. So here goes nothing. Make a new variable, x, for this sprite only. We'll use this to keep track of how far across the screen we've drawn. Set variable x to -240. The far left, and drop it into the top of our Raycaster custom block. Then we change variable x by. Now, over the course of this repeat FOV, we want the x variable to travel a total of 480 pixels, because that's the full width of the screen. So, to split that distance into FOV equal parts, because we're repeating by FOV, we divide 480 by FOV. Next, find the define single ray script. Remove the pen down and pen up blocks so that we no longer draw the 2D rays. To begin drawing our 3D scene, we need to know how far a ray has travelled, and therefore how far away a wall is. Scratch has a block for that. Distance to player. That will tell us the length of the current ray from the player to the wall. Let's make a new variable to store that in. Name it distance for this sprite only, and set the distance variable to distance of player. Super! Next we need to apply the perspective calculation to this distance so we know how tall the wall should appear on the screen. Make a new variable, naming it height, again for this sprite only, and then set height to some value divided by the distance. But we still need to fill in this left side, and this is known as the actual wall height, or size of the wall. This is a weird one really, as it's all relative, but for now, just enter the size number as 4,000. Yeah, it's quite big sounding, but don't worry, that should be about right, and you can play around with it later to see what effect it has. Now we have everything we need to draw a slice of wall. Bring in a goToXY block. The X position is simply the X variable. We created that a moment ago. The Y position can be our height variable. Now lower the pen to the paper. Pen down. To draw the wall, move the sprite using a set Y2, followed by 0, subtract height. So, if height was 100, then we'd now be drawing a line from a y of 100 to a y of negative 100. So then, pen up once more to complete the line, and our single ray is done. And by the nature of being called in a repeat loop, the next ray will begin to draw until the whole scene is completed. Oh man, yeah! We are in a position to run this baby. What do you think it will look like? Oh wow, now what is interesting is that you can really see these vertical lines. They are all very distinct. It's kind of hypnotic, like a really old console game. I love it though. We can still see the map where we were walking around overlaid on top, which is kind of funky at this stage, and even though we are just drawing lines, we can easily make out the 3D scene with its corridors and rooms. It's quite something how we have suddenly magicked up a virtual world from our simple level map. It really amazes me that it can be done so simply, and that really is the joy of raycasting. Right, to improve things further, let's hide the 2D map. Click into the level sprite. Now don't just use a hide block, that won't work at all. In fact, it would break the project since we are relying on touching blocks to detect the walls of the level. So instead use a set ghost effect block, set to 100. This causes the sprite to become completely invisible without actually hiding it, and yet they remain visible to the sensing blocks, just as we need. Yep, look at that. Very cool. So next we'll try to remove the gaps between our wall lines. So do we just want to bring the lines closer together? If I slide the FOV value, wow, that does the trick, but the level ends up being distorted, squashing the scene horizontally. What we need is a way of changing the spacing of lines without changing the field of view. This is often referred to as resolution, or just res for short. Make a new variable named res for all sprites. And at the top of the raycasting sprite, in the green flag script, set res to 8. This means we want every vertical line to be 8 pixels wide. Then make it into a slider, setting the minimum value to 4 and the maximum value to 16. We can instantly drop the res variable into the set pen size block. Oh yeah, you can see our level instantly fattened up, but we're not done yet. See how the lines still become gappy as we adjust the res slider. Let's see what the problem is. Come down to the Raycast custom block. These figures are now all wrong. We need to space out the lines based on the res variable, not the FOV variable. So how many vertical lines can we fit on the screen? Make a new variable, named scanLines. Set the scan lines to 480 that's the width of the screen, divided by res, the thickness of the lines. This is now the new value for our repeat loop. One thing leads to another, and we must also adjust the turn by angle. This wants to still turn by 5 degrees in total, so this becomes 5 divided by scanlines. The last value is the x variable, and obviously we want to move across by the width of the pen, which is res. Wow, what a reshuffle. Right, but do we have success? Run the project. It looks fine at a res of 8. Great. Let's slide that down. Oh, okay, we still have a small issue with gapping at odd numbers, but the even numbers all look to be really tight. This is probably due to where we begin drawing, so you see how the first line starts halfway off the screen. Let's try moving the whole drawing half a pen width to the right. Instead of setting x to -240, bring in a subtract operator and enter 240 on the right, and then on the left we want half of the pen width, that is res divided by 2. There, let's see if that fixed the problem. Yeah, awesome. That looks perfect now. What do you think? Let's have a walk around. Oops, too close to the wall there. Oh yeah, this is really coming together, and it's very fun to explore the level. But because it's all in one shade of blue, it can be a little hard to make out some of the turnings. A quick improvement we can make is to darken the walls as they move further away from us. Find the define single ray script, and look for where we get the distance to player. We want far away to mean darker. So from the pen category, bring in a set pen brightness block. In brightness terms, larger numbers mean brighter, so we are going to need to flip this number so that larger distances become darker. Bring in a subtract block, and we'll start from a brightness of 120. Rather than just putting distance right in there, we use a distance divided by 1.5 to make the level fade out a little more gradually. Feel free to play with these values. The larger the number we divide by, the more illuminated the level feels. Brilliant! You can see the effect that this has had on our 3D rendering. It feels so much more atmospheric. There's just so much more perception of depth. It's quite spooky, in fact. I don't think I'd want to be walking around this maze in real life, I can tell you. Oh, look at this! I especially love this room because it really shows off the perspective of the 3D projection. Right, we have an important adjustment to make now that many Scratch Raycasters, not all, but many, fail to implement. So look at this wall straight in front of me. But do you notice something weird? Is it just me, or does the wall look like it's curving away from us? The effect can be amplified if I whap up the field of view. Wowzers! Now you can really see the curvature. Ha, that's a crazy fisheye lens effect. And surprisingly, it's completely natural. Think about what we are seeing. Standing close to a wall, the distance to the wall directly in front of us is way closer than the distance to the wall to our left or right. So given that perspective says the wall further away appears smaller, it's obvious the wall should indeed curve away to the edges of the screen. But unless we want to feel giddy and get all motion sick, we should probably follow the general convention of most first-person computer games and apply a lens correction to straighten these lines up. Luckily, this is not very hard. The fix is to stop considering the distance from the eye to the wall and instead measure the distance from the wall to the player's view plane. This is defined by the direction the player is facing. We can always draw a triangle from the player to the wall, and then form a right angle from their view plane like so. If you've studied trigonometry, then you can calculate the adjacent length here using adjacent equals the cosine of t multiplied by the hypotenuse. Did I look that up on Wikipedia? Of course I did. Okay, let's code it up. We'll use another set distance block, and as the maths dictates, we'll multiply the current distance, that is the hypotenuse, by the cosine of... we need the relative direction of the ray. We don't have that yet. It's given by subtracting the direction of the player from this ray's direction. To get the original direction, come back to the define raycast script. We'll make a new variable, dir, dir, for this sprite only. And now set dir to the initial direction. Cool. So quickly back to the single ray script. And now we can subtract dir from the current direction. There, that makes the direction relative to the way we are facing. Splendid! This is just begging to be tested. Let's see what this effect has on our scene. So this is looking good. The walls do now appear straighter. Backing away, and yes, hardly any curve to be seen. Awesome! Now, while I go for a little walk around, let's have a think about what else we could improve. Gosh, I do hope you managed to get this far. It's just too much fun. Okay, what I think we should add is a floor and a ceiling. The pure black does make the walls appear a little floaty, since the walls appear to be bright close up. I feel the floor and ceiling probably should do the same. So click into the backdrop and then into the costume editor. I'm going to start painting a completely new costume and draw a filled rectangle to cover the entire bottom half of the canvas right up to the midway mark. Now that's cool. Look at the 3D scene. It already makes a difference just having a horizon. But I'm not quite sure about the colour though. With the rectangle selected, change the fill to be a gradient. I want the top colour to be black, but the second colour you can make a bit lighter, and any colour that suits your game. There. Oh, I like this, and the ground is more defined now. And yet it still feels like it's fading into the darkness in the distance. How about for the ceiling? Now we could choose a pure black for a night sky, but I think I'll just duplicate the floor. You can use copy and paste if you wish, or drag with the Alt key, and then finally flip it vertically. Yeah, there we go. Let's see that in action. Man, that's good. With every upgrade, it gets more immersive. Hold on, I just noticed the player sprite and raycasting sprites are still showing. We should have hidden these a while ago, shouldn't we? Click into the Raycaster sprite first, finding the when flag clicked. Just set ghost effect to 100 to hide the hitbox. We then do the same in the player sprite. Under the when flag clicked, set ghost effect to 100. Much cleaner. Right, let me just show you some other things that it might be nice to improve. Sometimes when you approach a wall, you'll see a significant jittering, like a wall edge can't decide whether to draw or not. Do you see that? Not the nicest, is it? Now remember I told you we could move our Raycaster sprite by 4 pixels each time so that it moved fast but didn't skip any walls? Well, that is only half the truth. Sure, we won't skip over a complete wall, but when moving by 4 pixels at a time, we can still skip over the edges of a wall. And that is what is happening here. Click into the Raycaster sprite and find the define single ray script. For a test, try reducing this to a move by 2 steps instead. Testing that does indeed show a great improvement in the jitter. Wow, but we do have to realise that the cost is that the Raycaster will now run approximately twice as slow as before, and that could be a bit too slow for some. So bear that in mind and consider whether you want speed over accuracy. Of course, you can always set the resolution to a higher number to keep things running fast. It's up to you. Now, since we're in this bit of code, there's another thing we can tweak. When I face a wall, do you see the slight wobble across the bottom? This is due to us sensing wall collisions to the nearest pixel. We can adjust this move -1 to be just half a pixel instead. Try it using move of -0.5 steps. And see how this improves the accuracy of the line. It's far smoother, isn't it? Again, this will have a slight impact on the speed of your Raycaster, but this time not as dramatic. But you can leave it at -1 if that does bother you. Okay guys, enough little fixes. We are close to complete, but I do have one more significant enhancement to show off, and it's cool. You may have noticed that although shading for depth works wonders for distinguishing between walls that are behind each other, it doesn't really help for corner junctions. See how the corner here has no line or difference in shade or colour to help us see it clearly. What I want to finish with is a way of colouring walls to distinguish them apart. Look at this diagram. We want all vertical walls to be colour A and all horizontal walls to be colour B. So, a ray collides with a vertical wall here. We want to paint the wall with colour A, right? But how can our Raycaster know this? Well, how about we paint another level costume? And everywhere we have a bit of colour, that means the wall next to it should be colour A. If I draw colour all down beside the vertical walls, then all I now need to do is check whether I'm touching this colour after a wall collision to know if I should paint colour A or B. This seems like a plan, but do you really fancy painting these colours in by hand? No, me neither. So let me show you a faster way. Start by duplicating the level sprite. Naming the copy as level colour. Okay, are you ready? You need to carefully follow these steps. In the costume editor, begin by making sure you are zoomed to 100% with the little equals button. Start by duplicating the level costume. We need to select all the shapes that make up the costume, either by dragging a selection box around them or by pressing Ctrl A. Next up, using the keyboard, press the right arrow key, just once. This will move the entire duplicated level costume slightly to the right. Now click the copy button, ready to make use of it again shortly. Got that so far? Great. Now we delete this entire costume. Don't worry, the copy is still there, ready to paste. Next up, select all the shapes that make up the first costume, again by dragging a selection box around it or pressing Ctrl A. But this time, with your keyboard, we press the left arrow key, just once, and the whole costume moves just that little bit to the left. And here we go. Finally, we press the paste button. This results in our left and right shifted costumes being laid out on top of each other in a single costume. You can see them both there. The magic of this is that we are left with the colour only to the left and right of the walls of our level, but not below or above. Just what we needed. Right then, so click into the Raycaster sprite. To detect the level colour, find a define single ray script, separate off the set distance script. We want to set the colour before this. Drop in an if-else block, and we'll check whether we are touching level colour. If we are, then we've collided with a vertical wall, so set pen colour to, let's go for 58. Else, we again set pen colour to 53, or whatever colour value you want, of course. Are you ready to test this? I most certainly am. Oh yes, this is so smart. The walls are really showing this effect off well. That's such a clean corner now. Big improvement. If I walk about, you can clearly see how the walls alternate between the two shades of blue depending on which way the wall faces. I've got to say, I'm really pleased with how this Raycaster has turned out. Oh, and here's my favourite room again. Look, even better than before. Awesome. The only problem with this technique of colouring appears on walls that are either curved or run at an angle. In this case, we tend to get a rather unstable flashing of colour. There is a solution though. Just come back into the costume editor for the level colour sprite. For walls that are not horizontal or vertical, we must paint the colours in ourselves. It's not really a problem. I'm going to draw a big rectangle through the middle of this circular level structure here, and then delete the circle part completely. Now, the coloration should be very well defined. Let's see that in action. Oh, amazing! The large circular pillar is now segmented into 4 areas by the rectangle I've just painted in. You could actually have quite a lot of fun colouring in levels the way you want to. What do you think? Wow, what a mammoth episode this has been. And goodness, have we made a lot of progress. We've gone from just having a 2D level and a player to a fully 3D game. Just like that. I really hope you've had a lot of fun following along. If so, then don't hesitate to smash that like button, and let me say I really look forward to taking a stroll through some of your levels. So continue to submit them to the Scratch Studio linked under this video. Now, if you haven't already, to avoid missing any future videos, subscribe to the channel now. We've just passed 100,000 subscribers. Woohoo! What a milestone, right? Thank you everyone, that just blows me away. And if you want to support my channel further to help me make these awesome videos, then please consider joining my channel membership. There's a lot of perks to be had, including more direct access to me through priority comments. You get the fun channel emoji, early access to videos before anyone else, and for those who need them, the Scratch projects themselves. But this is it. We've run out of time. Thank you for watching. Have a great week ahead, and Scratch on, guys.